Section 4.3, the mean value theorem. Before we will talk about the mean value theorem, let's talk about the other theorem that is called Rolle's theorem. Both of them, the mean value theorem and the Rolle's theorem, and along with the previous one, the extreme value theorem, and even the very, very previous one, intermediate value theorem, all of them are called existence theorem in mathematics. Because what they do, they are not really like, they are actually non-constructive in general. They will guarantee, this theorem will guarantee, like under the certain condition, that certain numbers exist. But they're not telling us directly how to compute these numbers. Okay, that's they proving that a number exists. And a certain number, like intermediate value or the extreme value, the Rolle's theorem talks about this. Let's see what number we're talking about here. Let f be a function that satisfies the following three hypotheses. Function must be continuous function on the closed interval, differentiable on the open interval. Of course, we're not including endpoints because derivatives, they do not exist at the sharp ends. And the value at the endpoints has to be the same. Okay, f of b equals to f of a equals to f of b. Then there exists a number c in AB such that derivative at c is 0. And derivative at c 0, meaning that tangent line has a slope 0. Slope 0 for the tangent line means horizontal tangent always exists under this condition. Right? That's mean I have the graphs on my other slide, but let's take it. Let's take a function defined on A and B, continuous function, and we can see the same value for A, the same value for B. Okay, and somewhere if the function is continuous and nice and smooth meaning differentiable, we have to find a point somewhere where the tangent is horizontal, derivative is 0, slope of the tangent 0. Okay? Always this number exists. And as I mentioned before, this theorem, these types of theorems are not telling us directly how to find this number, but is giving us a guarantee that this number exists. And sometimes it's enough for some certain condition or certain application. It's enough to know that we have this number. Okay, let's look at a couple different pictures. Maybe it's red color. We can see for the linear function, actually we have infinitely many numbers, actually all of the numbers, because derivative for all of the number on these between A and B is 0. That means we have infinitely many of these numbers. Yeah, this one is similar that I just gave you. This is the number C. We may even have multiple numbers happening. The derivative is 0, C sub 1, C sub 2, depends on the function. And this one is the upside down, also horizontal tangent, derivative 0, and function is continuous, and values and A and B are equal. Also, what is interesting to find out when I connect these 2 points, the endpoints, yeah, they also, since they have the same value, they will create a horizontal line. And thinking about the average rate of change between A and B, it will be 0. Yeah, that means I can also say the average rate of change, f of B minus f of A, B minus A, is exactly the same like that instantaneous rate of change at some point. Yeah? Because this is 0 and this is 0, but we have to find out where this situation is happening. We may use different skills to find out, but this theorem is telling us that this is possible. Yeah? But we know that since f of B and f of A is the same, we have 0 in the numerator, not in the denominator. And that's the Rolle's theorem. Okay. Let's look at this, for instance. Verify that the following function satisfies the 3 hypotheses of the Rolle's theorem on the interval between 0 and 9. Square root of x minus 1/3 x. This is the subtraction of 2 linear functions. Oh, no, of 2 continuous functions. That's what I was going to say. The root function and linear function. If we doing the algebraic operation on 2 continuous functions, we also getting continuity. So this is continuous function and differentiable between 0 and 9, of course, on the open interval. Did I type this? Yes, but we have continuity, we have differentiability and values. Let's say question mark. Did I compute this? I didn't compute. Let's check. Value at 0, square root of 0 times 0, of course, is 0. Value at 9, square root of 9, 1/3 times 9, 3 minus 3, 0. Yes, this is correct. Check, check, check. Yeah. I mean, definitely what we know, we don't know how function looks like, but we know that between 0 and 9, this is quite big interval. However, we know that definitely at some point, I don't know where, because if we will draw a tangent line will be horizontal. Derivative is 0. I mean, I don't know how function looks like, but let's say something like this. Oh, no sharp turns. Let's say maybe, okay, that's good. And then somewhere here, I can draw a tangent, and this is the point C. Yeah? Horizontal tangent, derivative at C is 0. What we can do, let's find out this number, okay? We have to find out where I can put x, derivative is 0, and that solution, that x will be the C point. Derivative. Derivative of the square root of x is 1/2 square root of x. Derivative of 1/3 x is 1/3. Yeah, nice and simple. And this one, oh, too fast. Derivative must be 0. Yeah, that's the derivative is 0. If this is 0, we may add 1/3 to both sides. We may cross multiply and divide by 2. So I'm solving for x. And now not taking the square root, actually squaring both sides. 9/4. 2 1/4. Oh, this will be 2 1/4, and this is definitely placed that number. We knew, even without solving, we knew that this value will be placed between 0 and 9. Okay, looks like we have the number. I'm almost right. 2 1/4. That's the way to solve. Yes, to get the number. Okay, but we knew that the number exists. Exercise number 2. Okay, this one I just decided to list a couple of functions, and let's just go really quickly through all of them, and let's check for which of these functions the Rolle's theorem is applicable. Okay, on the interval between -8 and +8. So what we need? We need continuity, we need differentiability, and we need the same value for -8 and +8. Okay, parabola x squared. Value for 8 will be 8 squared, and value for -8 will be also negative. Will be -8 squared, which negative taken to the power of even number becomes positive. Yes, this is correct. And function is continuous and differentiable. Yes, this is correct. We don't have to draw it. That's our best friend. Value for -8 and value for +8. And you can even probably say that this number is 0. And that's the 0. Derivative at 0 is 0. Okay, now let's go. X cube. X cube is not good because when I cube negative 8 and positive 8, different values. That means that's not good. X to the power of 1/3. We know that this function is not differentiable at 0. And actually, these different values, cube root of 8, cube root of negative 8, different values. But cube root has vertical tangent at 0. Negative 8 has different value. Negative 2. Positive 8, of course, has a positive value. Okay, and this is the thing at 0. Yeah? Derivative at 0 is undefined because vertical tangent. Vertical lines has no slope, no derivative. We know this, okay? That's not good. X to the power of 2/3, it's a little bit different function, which value actually at 8 and negative 8 will be the same because we're squaring. Yeah, we're squaring the number. Cube root of x squared, cube root of 8, 2. 2 squared is 4. Cube root of negative 8, negative 2 squared will be 4. So in value, we have no problem, but we do have a sharp corner. Derivative at 0 is undefined, then function is not differentiable. Yeah, we know we can't take it. Absolute value of x, of course, wrong. We have a sharp corner at 0. It's a v, not good. We don't even have to analyze this. Square root of x is not even defined on the negative numbers. That's not good. And then square root of 64 minus x squared. I hope we can, let me maybe write this, recognize this function as a upper part of the circle. Yeah, because if I will rewrite this, we will have, let's square both sides. And let's add x squared to the both sides. Now we all recognize this is equation of the circle. Yeah, but this is the equation of the entire circle. Now, if we will try to solve it for y, we will reverse it. We will subtract x squared. We will take the square root of both sides, but taking the square root of both sides, we will put plus or minus. And we only have positive. This means we will only consider the positive part, the semicircle, the positive part. And this is because this circle has a radius 8, 64, 8 squared. Okay. And this is nice and smooth curve, continuous, differentiable everywhere except the endpoints, but we're not including endpoints. And yes, this will be, let's come back, this will be good. Yeah, this will be good. Okay, and we have one more, come back, we have one more. X squared, quantity x squared minus 64, an absolute value of it. And that's interesting. Let's just double check if we know how to draw this function. When we place the absolute value of the entire value, what's happened? Let's consider this function. Parabola shifted 64 units down. Maybe it's not really, but this is 64. Okay, I mean we do have, and now that part of the parabola is above, because this is the quantity inside. Taking absolute value, yes, one more time, what we're doing, all of the negative values will become positive. Graphically, everything what is placed below the x-axis becomes positive. That's we have to do the nice reflection over the x-axis. Basically, the negative part disappeared, becomes positive. And this is 8, because 64, when we find the zeros, okay, that means this is the graph. And we, since we analyzing just the interval between negative and and 8, and negative 8 and 8, we're not even taking this part. But just in case, if we don't have this restriction, this will be the graph. And again, looks similar to that circle, right? When we cut the domain, it's nice and smooth curve, differentiable, continuous. Endpoints are the sharp corners, but we just end our interval. So yes, this is also a curve that satisfies the Rolle's theorem, and the values are the same. Good, nice. Yeah. All of the functions are the, like, we know basic functions. We have to know the graphs. Okay, let's keep working just for the future, for different things. Exercise number 3. Actually, now we know the Rolle's theorem, yeah, and I'm trying to exercise, but we're still waiting for the mean value theorem. Okay, one more exercise and then mean value theorem. Okay, proof that the given equation has exactly one real root. Okay, so what we can do. We remember, because this is like asking us, first of all, is asking to prove that just one real solution, one real root exists. We don't have to find out what is the root, because normally we can take this equation and solve it, but probably after a couple of seconds, you will realize it's not easy to solve this equation. Okay, that's when I will apply as a first step the first existence theorem, which was called intermediate value theorem. Yeah, we remember chapter 2, I think. Intermediate value theorem. What this theorem was telling us, if I will consider this as a function, x cubed plus x minus 1, and we want this function to be 0, that means we want this function, yeah, to intersect x-axis. I don't know where is this. Yeah. So what we will do, we can pick an interval, and we may have like lots of different solutions, but let's pick 0. I mean from 0 to 1, because actually I just draw it like kind of like this. I will focus on the interval between 0 and 1. 0. When we substitute 0, we have 0 cubed, 0 minus 1. The value is negative. When I substitute 1, we will have 1 plus 1 minus 1. Perfect, positive 1. And we remember, one value negative, one value positive. Actually, I even draw it, negative 1 and 1. Okay, so definitely one root exists. Yeah, but now we have to be careful. But this is just proving that the real root exists. If I still don't know if this is only one, because maybe the function is like, maybe intersects a couple of times, 1, 2, 3. We don't know how this third degree polynomial. Oh yeah, we don't have it, this blue. Okay, so what I will try, we can suppose that it has like roots, maybe on the like, let's take the interval a, let's take the value a and value b. So value at a is equal to value at b and is equal to 0. Yeah, that means possibly that I don't know, a and possibly b. Yeah, that means I'm trying to disprove that we have one real root. I'm trying to prove that we have more. Okay, now looking at this condition, this looks like the condition. I'm just assuming. This is the condition that we recognize for the Rolle's theorem. Also, function is continuous and differentiable. Yeah, but this is the case. Is this even possible? Because if I choose the interval a and b, and I'm saying that the value is 0, then I kind of have to, and function is continuous function. Yeah, I don't want to mess up our nice graph. Let's just predict the scenario a and b. Yeah, that will be another zeros. Then definitely function must go, for instance, up and down. or maybe, I don't know, maybe down and up, or maybe multiple times, maybe another zeros. But my point is function must increase and then decrease, or maybe decrease and increase, has to change the not the concavity, change the monotonicity. Yeah, function must be increasing or decreasing. So now what we can do, let's find out the derivative of this function. Derivative is 3x squared plus 1. And looking at this derivative, we may notice that this quantity is defined as a free quantity x squared, which is always positive, plus 1. This is always positive or eventually 0. Yeah, so if the derivative is always positive, okay, if the derivative is always positive, actually no, this will be always, this is never 0, always greater than 0, positive, then function is increasing, strictly increasing. Function is increasing on the entire domain. Okay? On the entire domain. So I mean, it's not possible for the function to like increase and decrease and come back. So I mean, if the function is just increasing, yeah, it's kind of like what I draw. It's no other option that the function will come back and cross the x-axis in the other place. No, because it's increasing. We will not analyze the concavity or other. That means this is not possible. Yeah, that's not happening. We don't have any other values. And basically this is proving that this function has only one real root, one intersection of the x-axis. Okay? Because this statement, yes, this statement is the contradiction to this. That means the equation cannot have two real roots. Okay, that means this is a little bit theoretical question, but nice to know that we may use intermediate value theorem and the Rolle's theorem. Yeah, no option. The Rolle's theorem is not working because we don't have 2 points that has the same value, the value 0. Okay, let's keep working. Oh, I have a little bit of notes. Okay, now the Rolle's theorem was like a special case of this. Let's finally look at this mean value theorem, which that's actually the section is talking about. Let's read the condition. It's quite similar to the Rolle's theorem. Let f be a function that fulfills two hypotheses. So function has to satisfy two hypotheses. F is continuous on the closed interval AB, and f is differentiable AB. Then there exists a number C in AB such that derivative at that C is equal to this, f of b minus f of a, b minus a. Or we may have this form, but I think we will stick to this one. So you can see now, since the values at the endpoints are not equal, this indicates the average rate of change, which if f of b is equal, and f of b and f of a is equal to each other, then this is 0, and this will be Rolle's theorem. But this cannot be the case. We may actually have different level of f of b and f of a. But then it's still telling me that instantaneous, did I type this? Oh yeah, I type on the other side. Okay, this is derivative, instantaneous rate of change. Oh, I'm pointing this. Yeah, this represents tangent slope, actually, slope of tangent. This is telling me that slope of the tangent line at some point is exactly the same like slope of secant line. Secant line connecting A and B. Yeah, they are the same. They are parallel. They are parallel. Okay. Okay. Now let's look at this scenario. We have a function. Yes, we have a function f of a, f of b, and I can find a point C that the derivative, which is slope of that line, slope of the tangent, is the same like slope of this one. And slope of this one is f of b minus f of a, b minus a. It's basically like we moved a little bit the special case, the horizontal, making this line like making different slope than 0, we create the mean value theorem. Or we may even have a couple of values, this one and this one. Yeah, then the tangent line has the same slope, it's parallel to the secant line, and secant always connecting the endpoints. Okay. Yeah, slope of the tangent line is the same like the slope of the secant line AB. That slope of the tangent, that slope of the secant. Yeah? And again, this theorem is just telling us that this number exists, C, or maybe C sub 1, C sub 2 exists. We don't know exactly how to, I mean, we may know how to compute it, but this theorem is not telling us. Okay. I have a couple of, yeah, that's been one of the nice like application is, let's think about the speed, velocity, to be more precise. Like for instance, if the car travels 180 kilometers in 2 hours, we can definitely compute the average speed, right? F of B minus F of A, the different, I mean, 90, because we just divide this distance over the time, 180 over 2, 90. But now the 90 is all over that 2 hours. Yeah, that's our trip, and this is 2 hours. The speedometer must have read 90 kilometers per hour at least once. Yeah? Because 90 kilometers is the average rate of change. That means this is this number, average rate of change. Meaning that at least once you have to, yeah, we have to drive 90. We didn't drive all the time 90 because it, of course, we slow down a little bit, we speed up. We probably drove even more than 90, but at least once, because driving like, I don't know, 70 not miles, kilometers per hour, and let's say 95 kilometers per hour. I'm supposed to say this. We have to, yes, in order to, this is continuity, we all the time driving, we didn't stop. So from 75 to 95, we have to go through 90, and that's this continuity. Okay. Okay, and also when we have some information about the values of the function, yeah, we may obtain the information about the derivative. This is like also nice use of this theorem. Let's apply. Exercise number 4, which is the first exercise for the mean value theorem. I mean, for the first one, what we have to do, use this graph of f to estimate the value of c. Where are the c's that satisfy the conclusion of the mean value theorem for the interval from 0 to 8? That's what I will do. This is 0, this is 8. First of all, I will create f of 8 minus f of 0, 8 minus 0. Slope of the secant line, which is this. I mean, we don't have to even compute. We may compute, but we don't have to. This is not really visible because we can go by the parallel, then the slope is the same. Now I have to find where I can place line which is tangent and at the same time parallel to the blue line. I will try, I don't know if I can, I think I can draw it somewhere. Oh, my parallel is not really, let's make it. Yeah, looks like somewhere here. Okay, of course, it's my estimation. 1, 2, 3, 4, 5, 6, 7, 8. So around the point C, let's say 2.6 because it's just 2.6. So derivative at C is the same like the average rate of change, the blue line, and C is approximately 2.6. Also, I can draw somewhere, probably you can see faster than me, a little bit more than 6, 6.2 maybe. Oh, 2.6, 6.2, funny. Okay, and I don't think we can draw maybe somewhere near to 0, but no, let's don't risk. Maybe we can squeeze some, but probably closer to 0. But definitely these points are the points where the average velocity, for instance, is the same like the instantaneous velocity. Oh, too fast. Okay, that's the point. Yes, like, I mean, that's the reason, the point, the meaning of the mean value theorem. Okay, another exercise. I hope you're enjoying this exercise. You may take a break, yeah, and you can pause the video and come back, but make sure that you know all of the exercise here. Always, right? Always. Okay, illustrate now what we have to do. Let's maybe, because I typed some of the questions, illustrate that the mean value theorem with f of x equals to square root of x on from 1 to 9. Okay, that's we have to just verify that this makes sense. Function square root of x is continuous and differentiable between 1 and 9. And yeah, let's illustrate this mean value theorem. Let's find graphically maybe, and maybe explicitly, the point C, because the mean value theorem is, oh, why I can't write? We have to find out the point C where f of 9 minus f of 1 over 9 minus 1 is the same. Yeah, that means slope of the secant line the same like the slope of the tangent. Okay, so what we can do? Oh, actually, I write this slope of the secant line the same like slope of the tangent. We need the derivative. Derivative of the square root of x is 1 over 2 square root of x, and I can substitute here. So this is I just typed the other way, secant line and the tangent line. And solving this, we may find that point C. Yeah, that means this is the way of, but again, this theorem is just proving that this number exists. And now if I can ask you what will be the value C without solving at the moment, we don't know exactly, but you can answer, you can tell me that the value will be between 1 and 9, definitely. And maybe even a couple of numbers, but we know the shape of the square root of x. It will be one number. Okay, let's solve it. Value square root of 9, 3, square root of 1, 2 over 8 is 1/4, cross multiply, dividing by 2, and squaring both sides, 4. Okay, 4 is definitely in that interval. And I have the graph. The slope, let's actually see, this is slope, right? Because this is the moment that we still didn't mix the left and the right hand side. That means slope of the blue line is 1/3. And slope of the tangent is also 1/3. 1/4, 1/4, right? That one. And because we can see derivative at C, and C is 4. When we substitute 4, we will have 1/4, 1/4. Okay, we make we illustrate. Okay, exercise number 6. Let me, how can I, okay. Okay, the same thing. Verify that following functions satisfy the three hypotheses of the mean value theorem, and we have nice polynomial x cubed minus x from 0 to 2. Polynomials are continuous, polynomials are differentiable, therefore definitely the number C exists between 0 and 2. And the numbers such that f prime at C equals to f of 2 minus f of 0 to minus 0. Secant line, tangent line, they are parallel. Let's find out, because it's still not complicated. Finding the derivative of this function is 3x squared minus 1. Instead of x, I can substitute c, 3c squared minus 1. Value for 2 is 6, value for 0 is 0. right? Value for 2 will be 2 cubed. You can do it, I know, I just using 2 cubed minus 2. Value for 0 will be 0 cubed minus 0. That's 6, okay? That's this. Subtracting 1, dividing by 3. Now taking the square root, we have positive and negative value. And this is fine, but we only looking at the positive since positive value is in that interval. Negative is somewhere else. If we will not restrict the domain to that interval, we can also, at this point, the slope is also of the tangent line parallel to the secant line. And I have the graph. Yeah, we can see that's the graph. That's the slope. This is the slope. Where is the slope? 3, because that's the point that we still didn't cross multiply. Yeah? And derivative is 3 at the point C. And C is here, 2 over square root of 3. A little bit different value, but okay, we found the point C. Let's look at the next one. Find the number C that satisfies the conclusion of the mean value theorem for the function x plus 1 over x on the interval 1/2 to 2. Okay, I didn't type this one. That's mean we can go a little bit slower. What you can do, you can pause the video and you can try to solve it on your own and then compare the answer. X plus 1 over x. Continuous function, differentiable function. 0 is a problem, but we're not looking at the interval which includes 0 from 1/2 to 2. Okay, so we're trying to, let's say x, f of 2 minus f of half, 2 minus half. Okay, as we will do this. I can put C, yeah, in the, because that I can keep x, but that C value is the point where the tangent is parallel to the secant. Okay, derivative. Derivative is derivative of this function. It's 1 minus 1 over x squared. Am I right? Because derivative of 1 over x is negative 1 over x squared. Okay, 1 minus 1 x squared, let's say c squared, yeah, because we're substituting c. Okay, value for 2, how can I organize this? Value for 2 will be 2 plus half, 5 halves. Value for 1/2 will be 1/2 and plus 2. Oh, the same value. Interesting. I mean, what we actually have a special case, right? This will be value for 2 is 5 halves. Value for 1/2, 1/2 plus 2 is also 5 halves. And this one will be 3 halves. Okay. Let's, what I'm doing. I mean, what's happened, we actually have the Rolle's theorem because the average rate of change between A and B is 0, because this is 0. We're getting the same values for 1/2 and 2. It's fine. This is still mean value theorem. Doesn't matter. Okay, let's substitute. Let's solve it for C. Let's solve it for C. Actually, c squared equals to 1, because we can flip the values and we can multiply by -1. C is plus or minus 1, but we're only taking 1 in this case, because quantity 1, C equals to 1, belongs to that interval. Okay, I don't have the graph, but 1/2 and 2, the values are actually the same, 5 halves and 5 halves. I mean, maybe, I don't know, something, maybe a little bit closer to 1/2. Okay, because the tangent line the point C, we've got 1. Derivative at 1 is 0, is the same like the average rate of change. And that was the, right? I mean, the C value is this, actually this one. Yeah, that's the secant line. Okay, C is 1. We found the number C. Let's keep working. Okay, what we have? We have another one. Suppose that f of 0 is -3 and f prime at x is less than equal to 5 for all of the values of x. How large can f of 2 possibly be? Okay, interesting. Yes, interesting question. First of all, we will not even think that we may use the mean value theorem. Oh, actually negative. Let me graph something. Value for 0 is -3, as we have -3. Now, we know that derivative for all of the x's is 5 or less. Right? It's 5 or less. That means derivative is the slope of the tangent. Slope of the tangent. So I can draw maybe that tangent. Okay? This slope is 5. 5 is the the maximum. The slope could be lower, right? Lower. But let's focus on the maximum, since we have to find the largest value. Okay, now 2. Let's say 2. How large can f of 2 possibly be? That's me. I don't know where is the 2 definitely can be on that tangent line, because since we have to create that slope, could be a little bit lower, if the derivative is, because that's the average rate of change, must be the same like the slope of the tangent line. I mean, must be probably a little bit lower also, but since we're looking for the highest, let's keep that point. And I think we don't even have to, we will do explicitly, but we don't even have to do explicitly. We can read, we can find out this value. We have lots of information. Let's figure out. We may define this as a rise, which is just 2 units. Because it's from 0 to 2, and run, we don't know, because we don't know f of 2. But run is basically f of 2 minus -3, which is, it's that whole distance. 3 units and f of 2. We have to just add 3 units. And we know now, we may think this way, that run, the whole value run, or delta y, it's more professional. This, when I did what number, I'm looking, let me, that value divide by 2, yes, we have to get 5, because slope for it's 5. Right? That's mean what number divide by 2 is 5. Oh, yeah, okay, yes, what number divided by 2 is 5? Of course, it's 10. That means this has to be 10. And if we have 3 units, this is supposed to be 7 units up. We figure out this is the maximum value of f of 2. And I kind of use the, because slope of the tangent, the same like the slope of the secant line. I use the information. But let's just see what I will assume, yes, we are given that f is differentiable because derivative exists, therefore is continuous everywhere. In particular, we can apply the mean value theorem on the interval from 0 to 2. And let's see what I did. I started with the theorem, f of 2 minus f of 0, 2 minus 0 equals to f prime of x, f prime of c, but I can use x. Now, f of 2 minus f of 3, 2, and I pick the derivative 5, the smallest value, right? And f of 0 is -3, this is 2, subtract that, and we can see what we're getting. 5, the slope equals to the slope of the secant line, which we can't complete it because we don't have f of 2. However, when I multiply by 2, we can see the same thing. F of 2 plus 3, that value plus 3, because that will be the run line segment, must be 10, because 10 divided by 2 will give us 5. Okay, f of 2 is 7. But we did it without even using explicitly the mean value theorem. Okay, that means the largest possible value, but you may start right away this if you figure out that the mean value theorem is applicable. Okay. Oh, wow. Okay, what I have, let's see. I have another one like this, but please, pause the video and look at the solution. I can skip this one because I did solve it. Okay, the largest possible value f of 7 is 51, but you may draw, okay, you may draw the graph here. Please do this. All of the information between 1 and 7. Okay, I can leave it for you. Now what I have another one, the same thing. Since derivative exists, you may pause the video and look at the solution. That's we prove that this is right. And then I have another one. I love this type of question. You may also draw it. Okay. The same idea. And okay, that's the, and I have 2 more problems that I will not skip it. We will solve together. I have exercise 12 and 13. They will also be helpful for your homework assignments. Okay, let's see. What do I have? A copy from your homework assignments. The mean value theorem is non-constructive for generic function f, meaning that it offers a guarantee that there will be a some number c in AB, so that f prime at c equals the average rate of change, f of b minus f of a, b minus a, but gives no indication of how to find that c, other than going through the process of solving the equation, using the algebra. There are few cases where the value of c is nice, which this problem considers. Work through the calculations underlying the following claims. I mean, what this question is telling us, we have 3 different functions, a, b, and c, and we are given, I'm assuming, that's what, we are given the value c. At least here we are given the value c, and we are given the value c here. Okay, actually here. Okay, and are we given the value c? Actually, we're given because it's telling us that f prime has the desired value at every number. Okay, that means c is actually all of the numbers. C could be the nx in the interval. Yeah, c is basically nx. Okay, in that interval. Okay, but what we have to do? We have to take these functions and basically calculate the value c. Okay, we can do this, and then we have to prove it that this c is the same as the given one. Okay, let's look at the part A. I can maybe I copy part A. Suppose f is a linear function, mx plus n. In this case, f prime has the desired value at every x value in the interval. Of course, because if we will tell the slope of let's start. F prime at c equals to f of b minus f of a, b minus a. And for the line, Yes, for the line, the average rate of change or instantaneous rate of change, it's still the same because line has a constant slope. And we know what's the derivative of the linear function mx plus n. The derivative is the slope m. That's the derivative. We don't even have to yet. It's compute. We know that this is the slope. But let's just prove it. When I substitute instead of xb, we will have mb minus plus n minus, when I substitute a, ma plus n. Right? B minus a. mb plus n minus ma plus minus n, distributing. This is cancel out. Then we can factor out m, b minus a, b minus a. And of course, we're getting m. We're getting m as the average rate of change. And at the same time, yeah, this is derivative always. It works for every value. We can see derivative is, we actually have the derivative, and we can say that this works for all x's in the domain. And actually domain is all of the real numbers, for all of the real numbers. Right? But we did prove, we can see through the right-hand side of this mean value theorem, we claim that this is true. Yeah, we got m. It's funny. The average rate of change, the same like the instantaneous rate of change. Okay, but situation is a little bit different. And I can draw a function, but we don't. Yeah, the linear function a, b, okay, and f of b, f of a, and then c could be the slope is the same, and because that's the slope, f of b minus f of a. It's of course the c could be any number, because if I will draw a tangent line, which actually tangent line to the line is the same line, it's any number. Okay, that means any c in AB satisfies this. Okay, now let's look at part B. Suppose f is a quadratic function, kx squared plus mx plus n. In this case, f prime of c has the desired value at the arithmetic mean, the average mean, of course, the average rate of change of a and b, and for instance is this value. Yeah, we have to prove it. A plus b over 2. Yeah? It is the only number so that c minus a equals to b minus c. But we have to prove that at this point, yeah, that's what we're saying, at this point, the derivative, again, I can write, at that point, f prime of c, and this is the point we can check, is exactly the same like f of b minus f of a, b minus a. When I take the derivative and substitute that value, yeah, I can, let's do it, let's work it out first of all, the right-hand side. We will get right and left the same. Okay, let's figure out the right-hand side first. F of b. Instead of x, we have to substitute b. K b squared plus m b plus n, and then minus f of a. Yeah. Instead of x, to the equation of the function, I can indicate in blue, then we will know what I'm doing. Instead of x, we placing a. K a squared plus ma plus n, b minus a. K b squared mb plus n minus k a squared minus ma minus n. That's gone. Now we can Factor out k will be b squared minus a squared. Yes, I took these terms, and we can also factor out m, b minus a. Yeah, by grouping, I'm trying to get the factored form. Now this is k, b, b squared minus a squared. Now we can see a little bit of algebra. B minus a, b plus a, plus m, b minus a. And that's actually b minus a. Now I can factor out the common factor b minus a, b minus a. So what we will do b minus a, and then what's left? K, b plus a, plus m, because the green part is outside. I factor out. And this happened, of course, being the same factor in the denominator, we can cancel out. Oh, I wish to have one extra line. But what we got, we get actually I can keep that form. K, b plus a, plus m. Okay. So this looks like this quantity, like if the coefficients are given k and m, and of course the point a and b, because that's our interval a, b, we have to prove, okay, that derivative at the given point c is the same like this form. Right? So what we can do, derivative, let's use here. Derivative, I can write derivative. Derivative will be 2 kx, yeah, derivative of f of x. I'm trying to find out derivative, plus m. Makes sense? I can maybe write here, it will be 2, because derivative of x squared is 2x times k, mx is m, and plus 0. Okay, but actually my x is c. Yeah, because that's the value. And now 2k, and we can substitute that value. A plus b over 2 plus m. We can cancel out 2, and we're getting k plus ab equals to m. Yes, which actually I could. Yeah, I'm just wishing to have one extra line. This is the same like this one. That's when we can say, yes, this is the value C that satisfies the mean value theorem. The average rate of change, we've got the same. And if we will draw this situation, we will have quadratic between A and B. Okay, value for A, value for B, and parallel. This is our C value. Okay? And the C value actually it's exactly AB over 2. Okay? And then derivative at AB over 2 is exactly the same like the average rate of change. We claim that this is, with that value of C, we satisfying this condition. Okay, and let's do one more. Suppose f is a function of the form a over x, just for the positive x's, then f prime at c has a desired value at c equals to square root of ab. Okay, and the same thing. Note that c square root of ab is known as a geometric mean, okay, of a and b, and is the only positive number, so that c over a equals to b over c. Okay, this is just additional information, but we will prove it. Okay, we will prove it that the average rate of change is exactly the same like the instantaneous rate of change derivative at that value c. Okay, let me plan. That means derivative at c is equal to f of b minus f of a b minus a. Okay, I can work on the right hand side. Okay, value of the function for b. I have to place instead of x, b. A over b. A over a. B minus a. Okay, and then we can factor out a. It will be 1 over b, 1 over a, b minus a. When we get a common denominator, we will have a minus b, a times b, b minus a. A minus b, b minus a. This is just algebra. And when I simplify this, I will get -1 because they are opposite. Okay, that means the value that I received as a slope of the secant line is -a over b. Okay, now we have to prove, yeah, that's the slope. We have to prove that the derivative at the point square root of ab match to this right hand side. Okay, what is derivative? Derivative of the function f of x, it's the constant a, and derivative of 1 over x is -1 over x squared. Okay, that's me, we will have negative, let me write nicely, negative a over x squared. Negative a over x squared. Okay, negative a over c squared. Negative a, and c is square root of ab squared. When we square the square root, we will end up with ab. Yes, we prove that this is the same. Yes, we prove that we claim that this is true. That's c value. And we can try to, hyperbola 1 over x looks like this one, and between a and b, let's pretend this is a, this is b, and looks like negative, right? Somewhere here will be the value c, and value c is defined as a square root of quantity a and b. Okay, we did it. Let me just double check. Oh yeah, it's like the arithmetic mean, but okay. And I have one more. Let's really quickly, I know that the session is really long, but as I said, you may watch this, yeah, you may watch this, you may make the pause and just look at the question. Okay, determine f of a and f of b, and the average rate of change f of b minus f of a, b minus a for the function tangent of x, where a is pi over 3 and b is 2 pi over 3. Then explain how you can be sure that there is no number c between pi over 3 and 2 pi over 3 that makes derivative at c equal to the average rate of change, and why this does not satisfy the mean value theorem. Probably without even starting, you may tell the answer. Yeah, we can do it explicitly, but when we will draw tangent, we know that tangent function has discontinuity. Tangent is not defined at pi over 2, and actually, and so on. Yeah, that means this is pi, this is 3 pi over 2, 0. Every pi over 2, we have a vertical asymptote. That means this is tangent. And we have discontinuity because our interval is asking, the interval is asking for pi over 3 and 2 pi over 3, 60 and 120, which is closer to pi over 3. Yeah? When I combine this, actually, that's not, yeah, that's nonsense. We can't do this because we have discontinuity. Function is not continuous, function is not differentiable inside that interval. So we're not even satisfying pi over 3 and 2 pi over 3. That's how I will, yeah, start. But since the question is asking, let's find the value at a. Let's see what we will get. Value at pi over 3. Tangent at pi over 3. Now, yeah, you may answer first, square root of 3. Then b, value 2 pi over 3. 2 pi over 3, the reference angle is also pi over 3, but since it's the angle from the second quadrant, tangent is negative in the second quadrant, then will be negative square root of 3. And we actually make sense. Positive square root of 3 and negative square root of 3. Okay, we have this, and now we will try to compute f of b minus f of a, b minus a. Let's see what we will get. Because this supposed to be the derivative, but okay, f of b, f of 2 pi over 3 minus f of pi over 3, 2 pi over 3 minus pi over 3. Okay, f of 2 pi over 3 was negative square root of 3 minus positive square root of 3. And this is just 2 pi, 1 pi over 3. Okay, that's we getting negative 2 times 3, negative 6 square root of 3 over pi. We're getting a negative number. And now the question was, this supposed to be the derivative at some point, yeah? Because again, this is the mean value theorem. If we would like to contradict derivative of tangent, yes, whatever you said is correct. Of course, I don't know what you're saying. It's secant square of x. Yes, and secant square of x is always positive. That's how you will realize that something is wrong. We cannot get negative. That's not possible. Yeah, that's not true. Not equal to. And then you will think, why we're getting something wrong? Because function is not continuous, not differentiable, and we will not use the mean value theorem because function doesn't satisfy this condition. And then this theorem is not giving us this guarantee. Okay, that's everything for the mean value theorem. You may watch this session a couple of times. You may just pick your favorite question and watch over and over again and practice, of course, the question. And yes, good luck with your mean value theorem. Thank you.